actions in Rosie. So if you haven't heard of Rosie, Rosie is a project that we have here at the university, which we use to investigate a lot of different things, but primarily interactive task learning. And interactive task learning is a relatively new kind of challenge problem in AI. And the goal is to design agents that can learn new tasks from scratch through natural forms of interaction. So the idea is that you can have a robot or an agent that you can just teach new tasks very quickly with, just by interacting with them like you would a person. And we focus on a variant of this, which we call situated interactive instruction, where the robot and the person are situated in the same environment, so they're interacting with each other, and where the agent primarily learns through natural language. So we focus on kind of teaching through English. To kind of give a quick flavor of what this looks like, here's kind of a demo in one of our simulator environments. I'm going to teach the robot to store the cola, and immediately the robot doesn't know what cola means, and so this is kind of a back and forth where I can say, if the object is a red soda, then it's a cola. So the agent's able to initiate new questions when it's missing knowledge. And I'm going to say to store the cola, if it's a drink, then put it in the fridge and then close the fridge. And then given this goal, the agent just goes off. It's able to do some planning and figure out how to put together some actions that'll achieve that goal. And so this is kind of what things look like in Rosie. It's a lot of, again, back and forth interaction and learning from instruction. And there's a couple kind of key characteristics of learning from this way. But I think one of the biggest ones is that the agent has to learn very quickly from just a few examples. So that means that the learning has to be as efficient as possible so that it maximizes the learning from each instruction. It has to generalize very well to be able to apply what it's learned in one situation to another. It has to be able to compose knowledge from one situation to another, and it has to learn a diverse range of different kinds of tasks. I think this is really what motivates our approach in using SOAR and using cognitive architecture and a lot of symbolic reasoning, is because we are trying to learn essentially from one shot, right? We have one example and we're trying to learn a task and be able to generalize it. And that really, I think, motivates the use of SOAR as opposed to other kind of data hungry algorithms like deep learning or other things like that. And when we look at SOAR, SOAR really provides a lot of mechanisms that we use in Rosie, and we take advantage of all the different knowledge and memory systems that it has to store the different things that we need. And you'll kind of see as we go on where these different memories come in as Rosie learns new tasks. But kind of as John showed, we have applied Rosie to a lot of different domains, different robots, different simulators. So this approach is fairly general. And if you are curious about learning a little bit more about Rosie or about interactive task learning, there's some good resources at soargroup.github.com/Rosie, the link there, which you can take a look at. But I'm going to focus today on sort of my part of research in Rosie, which is looking at task diversity. So if we look at, here's a kind of a sample of some different tasks we might want to teach the agent. And if we look at it, we'll see that these different tasks will have just a wide range of different characteristics and objects and concepts that are involved with learning these different tasks. And so we want an approach that will be able to handle this range of different characteristics and actions and strategies that the instructor might use. So my work has kind of been taking, how do we expand the method that we do for learning tasks and really try to tackle some of this diversity that exists in the tasks that we want to learn. And I've focused on kind of these three main dimensions, which are different types of actions, different ways of modifying a task, or different ways of formulating a task. But today I'm going to focus on just the first one, which is learning diverse action types. To kind of motivate this, why this is important, consider the task of telling Alice a message. So I want Rosie to tell Alice a message. And as part of this task, the robot's going to have to use communication. It's going to have to ask or listen for the message. It's going to have to tell or say the message out loud. This involves perception. It might have to go find Alice. It involves memory. The agent's going to have to remember the message so that it can tell it later. So it's not just doing these kind of more complicated tasks. They don't just involve physically manipulating things or picking things up, but really we want to get at these different types of actions. And to, if we look at, say, the 20 most common verbs, we can see that there are these verbs kind of show that same diversity. So there's verbs that talk about physically doing things in the world, movement or perception, communication, and mental actions. But so far, I would say that especially in interactive task learning, the last two especially have been relatively understudied. So most people are doing research and their agents can do physical actions, moving around, maybe doing some perception. But really thinking about how do we have an agent that can learn tasks that involve communication and mental actions even, is something I think is a contribution of the work that I've been doing. So kind of the key research question to ask is, how can an ITL agent such as Rosie learn tasks that have these different types of actions in them? And how Rosie works is that Rosie learns tasks by building up compositions of this simple or the innate tasks that it starts with. And so if we want tasks that show these diverse types of actions, we really need to think about how do we create an initial or an innate set of tasks that the agent can learn that have also these different characteristics. So in Rosie, we have a lot of different types of actions. We have picking things up, opening doors, moving around. We've even added actions that involve perception. So the agent might have to find an object or might have to look around the room, which we call scan. But we're going to focus on really these two types of communication and mental actions, which I think kind of sets this apart. So for communication right now, we have two actions. The robot could just say a message to a person, or the robot could ask a question and then record the answer in its working memory. And then for mental actions, we have kind of the two main ways, right? So we have remembering, which is where the agent will store knowledge either in its working memory or its semantic memory. And then we have the action of recalling, where it retrieves this knowledge from one of these two long-term memories. But it turns out that adding these types of actions to Rosie, it was fairly challenging and sort of introduces these two types, kind of introduce new problems that we had to address. But to kind of get at what that is, I'm going to first talk a little bit about how Rosie learns task policies. So when Rosie learns a task, or when Rosie represents a task, it has all these different types of task knowledge. So it knows about the task arguments that it requires, the goal of the task, when the task should be proposed, and when to do each action, which is the policy, and then has a model of these tasks or these actions. We're going to focus on the task policy, which we mean a state-based rule that says when to perform a certain subtask. So these rules say, in this state, this is the action that you should do or that you should prefer. So instead of having a fixed procedure, although we can learn procedures, but when we talk about learning policies, we have this very kind of flexible representation where what the agent does next is dependent on the current state. And what that means is that it can have policies that address kind of different circumstances that come up and can adapt to them. So if the state kind of changes in a different way or an unpredictable way, the policy, along with goal reasoning, can help it kind of navigate that and do the right thing. However, being able to learn a task policy, as we'll see, requires rich domain knowledge. It has to have models of how its actions affect the world and how they change the state. So it does require more knowledge to be able to learn. But again, it's kind of a more flexible than just a simple procedure, which is kind of fixed. So just to give kind of example, we're going to talk about the task of teaching to discard the soda, where we give it the goal that the soda is in the garbage. And then once we give it the goal, the agent can use its reasoning and planning to figure out a sequence of actions that will achieve that goal. So it'll pick up the soda, approach the garbage, and then put it inside the garbage. And it's able to do this if it has models of what these actions do and also proposal conditions. So when these actions are valid. And if it has that knowledge, it can formulate a plan that will achieve the goal using fairly simple forward search. But once the agent is done with the task, what we do is we go back and we try to learn policy, again, these policy rules using source chunking, or explanation-based learning. And the key insight is that if the agent can explain why the actions helped it achieve the goal, then it can chunk that knowledge into a rule that will tell it when those actions should be preferred. So once the task is done, we use the agent's episodic memory, which captures a history of the different states throughout the task and what actions were performed in between. So the initial state, and then what the state was after we finished pickup, and so on and so forth. And then we can use this to learn these policies. And we kind of work piecemeal, so one subtask at a time, and we work backwards to forwards. So first we're going to retrieve the next to last state, state S2. So we're going to retrieve that from mem, create a copy of it, and then we're going to propose all the possible actions that we know how to do in that state. So it could be picking something up, it could be opening a door, it could be driving somewhere. So we're going to propose all the things it could do, but of course it doesn't have a policy rule that says which it should prefer. And so you heard a little bit of John talking about impasses. We hit a tie and we go into a substate. And then we use the selection space to, normally we try to do a search maybe to evaluate which of these should happen. But what we can do is we can break that tie by saying, I want to evaluate the operator that we actually did. In this case, we actually put the object into the garbage, and so that's the thing I'm going to evaluate. So it goes ahead, in order to evaluate it, it creates a copy of the state, it simulates applying that action, in this case, putting the object in the garbage. It has rules that say how that changes the state. So we simulate the action, and then if we detect that, hey, the goal is satisfied, then we can return success. And again, through source chunking, when we return this success, we end up learning a rule that gives that operator a best preference. So the rule might look something like, if the task is discarding an object, that object is currently grabbed, and there's a garbage which is within reach, then prefer putting that object in the garbage. And so this is, again, kind of an example of what we're talking about with one of these policy rules. So we learned a policy for the last action. We work backwards and we do the second to last. A very similar procedure. In this case, we retrieve state S1. We go through evaluate approach, and we end up learning a policy rule that says when you should approach the garbage, which is probably when the soda is already picked up. So this is how it ends up learning these policies. So going back to what this talk is about, we think, okay, how do we learn these sorts of policies, or how do we learn policies in this way when we're using mental and communicative actions? And there's sort of two problems that arise. Well, and the problem is that there's very difficult to have a priori proposal and model knowledge for some of these tasks. So what do I mean by that? Well, these tasks involve, again, communication and mental actions. And it's very difficult for the agent to have a model, a complete model of using its memory or communication. That just requires a lot of knowledge. And if we think of, say, proposing something, we have the ask action, right? But how does it know what to ask? There's practically an infinite amount of things that it could ask at any one time. So having a proposal rule that says ask this question or ask this, it's just not something you could search through. We're talking about action models. Say we have an action like recall, where it's retrieving something from long-term memory. Well, it can't possibly have a model of what will happen or what will be returned, because that knowledge is in long-term memory. It's not in working memory. And so whether or not something is returned, the agent doesn't have knowledge about what'll happen there. So these just end up being very difficult to incorporate into the standard forward search and explanation that we need in order to be able to learn these policies. So how we address that. So first, for the proposals, this is fairly straightforward. Instead of having a priori proposal rule, we just learn from the instructor when we should do these things. So we're never going to try to do ask unless the instructor has told us that's an action you should do. So in this case, we say, tell Alice a message. The goal is that Alice heard the message. And then the instructor will say, okay, first ask, what is the message? And now the agent can take that and learn a new proposal rule specific to this task, where it says, if the current task is telling somebody a message, then ask the question, what is the message? And so essentially for each instance of these communication or these mental actions, the agent will learn a proposal rule just specific to that use. Second, when we talk about learning action models, instead of having a model to begin with, what we can do is we can use an example from the agent's history or experience to kind of act as a proxy for that model. So in this case, once the agent asks, well, what is the message? Let's say I respond, the message, the meeting is canceled. So what the agent can do, the agent now has an example of when I ask this question, I will get this kind of response. I will get the response of the meeting is canceled. And it can use this to then learn an action model that'll kind of incorporate this knowledge. So back to our learning that we saw before, when we want to simulate the ask command, we don't have a model. And so we end up hitting an impasse because we don't have that action model. And then in the substate, we can look at episodic memory and say, okay, what actually happened when I asked this question? Okay, I got this sentence back. All right, I'm gonna now learn a model that will incorporate that. And so that might be something like, if the current task is to tell somebody a message, and I ask the question, what is the message? Then I'm gonna add this new sentence to the world saying the meeting is canceled. So I sort of learned one instance of this model, but it turns out that that's sufficient for being able to model other tasks in the future. Now there's a difficulty that arises when, or it may seem like there's a difficulty when there's different possible things that could happen. So in the previous example, going back, when I ask, what is the message? I'm always going to get a sentence back, or I'm expecting to always get a sentence back. But what happens if different things could happen? So in this case, the robot's looking for Alice, and I'm going to try to say, do you know Alice's office? Or I'm going to say, recall the office of Alice. And if that recall was successful, do one thing, go there, go to the office that you remembered or recalled. But if you didn't recall anything, like you didn't know where Alice's office is, then just explore until you see that. So it might seem like we now need an action model for each of these two cases. But actually what we find is we only need one of them in order to, we only need to generate a possible explanation from beginning to end. We don't have to cover every single case. We actually only need one valid trace. And so if we only learn one action model for recall, in this case, that ends up being sufficient given the way that we learn policies. So we're actually able to do this, and the real benefit here is that we now have action models for these things like recall or ask, which means the agent can use them to search if it encounters new situations it didn't before. So to kind of finish up, I'm going to show all these things being put together into a demo. And in this demo, we're going to have Rosie serve somebody a drink. And we're going to put together a couple of these pieces. So we're going to say, if Rosie already knows their drink preference, then go up to that person, confirm it's what they want, and then go get it. If they don't know the drink preference already, then go up to the person and ask what they want. in either case, get them the drink, and then finally remember what they wanted in the future for their drink preference. And you can see, so this is a fairly complex task that involves asking questions, remembering things, using its knowledge, and the agent doesn't need to know how to do it needs to know how to do them, but it doesn't need to have a full model ahead of time about how it can use its memories or how it can communicate. It's actually able to learn that from the instructor giving examples of what it should do in this circumstance. So here's an example of this demo in our other simulated world. So the agent is going to start off, and we're going to say, okay, serve Mary. Agent doesn't know what the goal is. And so we say, okay, the goal is that Mary's holding a desired drink. Agent doesn't know what to do next. And so here's the first step, recall the preferred drink of Mary. And so here the agent does that. And then I'm going to say, if there is a recalled drink, meaning like if you did retrieve something or you did recall something, then ask Mary if that's what she wants. Oh, sorry. Come on. So again, what we're saying is if you did recall something, then label that or remember that as the desired drink. And now that connects to our goal of, in this case, the soda. So the agent's going to ask Mary, do you want a soda or soda? She says yes. And we say, if the answer is yes, then remember the recalled drink as the desired drink. And so now the robot knows, okay, the soda is the desired drink. I'm going to go get it and give it to Mary. Finally, we say, permanently remember the desired drink as the preferred drink of Mary. This essentially will remember soda in the future as Mary's preferred drink. Okay, next, we're going to say serve Alice. In this case, Rosie tried to recall something but didn't. And so we can say, if nothing was recalled, then ask Alice, what drink would you like? But the agent can't find Alice, it's not in the room. I can say Alice is in the main office. And it's sort of maybe even overlooked, but the agent did this find action it didn't do before. But it was able to do that because it's able to do this kind of planning and reasoning. All right, so the agent asks Alice what she wants. She says a soda. We say, okay, remember what she said, remember the answer as the desired drink. And the agent's able to go get the water and give it to her. Okay, then we say serve Bob. The agent knows where Bob is, so it goes back. It's going to ask Bob if he wants juice or soda. Bob's going to say no. So soda was his preferred drink. Then we say if the answer is no, then ask Bob what drink would you like. But notice now the agent's able to finish the rest of the task without any more instruction because it's able to learn from the examples before. And it's able to do that specifically because it has a policy of how these actions actually help it achieve the goal, instead of just relying on a fixed procedure. So to kind of finish up, at the SOAR workshop, we like to do nuggets and coal. So nuggets, so again, we've kind of showed that the agent is able to learn pretty complex tasks that do involve mental and communicative actions. And it's adding these new actions, we're able to overcome some of the unique challenges of using them with this EBL approach to learning policies. And we can do this without requiring highly specialized knowledge of how communication works or how memory works. We're sort of able to teach it strategies for dealing with those. On the coal side, there's still kind of a narrow range of valid uses for these actions. So remembering, recalling, asking questions, there's only kind of a couple of ways that they can be used as of now. And as maybe you saw from the video, the instruction uses pretty precise wording, which is maybe not supernatural. and it does require kind of an expert to know how to teach the system. So while it is natural language, it's a fairly restricted natural language. And we'd like to kind of expand that more in the future. And another thing is that the agent cannot currently learn new innate tasks. So as I said, Rosie can learn tasks that are composed of the innate tasks, so ones that it starts with, but it couldn't learn a brand new task that wasn't dependent on any other. So that I think would be an interesting avenue for future work. So that's my talk. So I don't know if Peter, if there are any questions in the chat, I'd be happy to answer them.
Yes, Aaron, we still have a few more minutes, and I've got a couple of questions here. First of all, Nate Durbinski asked, I'd be curious what is inherently different about verbs that relate to physical manipulation and movement, which is also physical manipulation, but of the agent.
Yeah. So I don't know if there's necessarily a hard distinction between those two, and there are some that kind of are a little bit of both. So I'm not sure I would draw an extremely hard line, but I would say, at least in Rosie, one of the main distinctions is that often with like a physical action, or what I call a physical manipulation action, like pick up or open, there's a very clear change in the external environment. Whereas with something like turn right, while the Rosie just doesn't really have a great way of being able to represent how that will change the world, given its kind of symbolic representation. And so those sorts of things tend to be a lot harder for it to model. But I don't know if that's like necessarily a clear distinction in terms of the verbs themselves.
Okay, thanks. And there's another question from John Laird. Can Rosie learn any control structures, such as things like while loops?
So a good softball question from my advisor trying to brag about Rosie. Yeah, so we've done other work that has done learning that involves certain looping, if statements, being able to choose kind of between two different actions. So we have been able to kind of incorporate certain things like that. And this talk was mostly about learning tasks that have goals, or they're represented as achieving a goal. Whereas we've also done a lot of work with learning procedures, which do have kind of these more complex control structures that we can have.
Okay. Well, I don't see any more questions in the chat. We still have a couple minutes if anyone wants to post a question. And we won't start the next talk for another minute and a half. So you did such a great job, Aaron, of answering all the questions. Good to see we have over 60 people connected out there. So
there is a new question. I'll just bring it in by Bob Mariner. Does this kind of approach support maintenance goals that need to be continually attempted or to be achieved?
Yeah. So that's something we've definitely thought about adding, and I don't think would be all that difficult within our framework, but it's not something that we've done so far. So essentially, we can have a representation of the goal, and we just need maybe a way of saying, once you've achieved that, just kind of wait. And then if that goal becomes unachieved, then you can take more actions to try to achieve it again, or kind of keep that from happening. But no, that's not something that we've currently done yet.
We have one other question from Justin Lee. What would happen if recall gets the wrong thing, e.g. due to activation difference?
Okay. So
you're running out of time.
So just very quickly, so for SMEM, we are, in general, it's probably not going to, we're not relying on activation, essentially. It's fairly unambiguous what it's going to retrieve, although if if you stored kind of more things than we currently do, if you kind of had it remember a lot of different things, it's possible there might be like a tie between those, or there might be multiple valid retrievals. In that case, we wouldn't necessarily have currently a great way of distinguishing them. But I'll turn it over to James.